Welcome to the wonderful world of physics. This is section 17.3, thermal expansion. In general, materials expand when they're heated up, and we're going to talk about that in this section. For a gas, you've already seen the ideal gas law. PV equals nRT means that when you raise the temperature of a gas, everything else being kept constant, then the volume will increase. Volume is proportional to temperature. So if you were to double the temperature of a gas, you get double the volume. There's a similar expansion for liquids and solids. However, because liquids and solids, those molecules are bound to each other, then it's not as pronounced an effect. You will usually get that expansion, but it's not so much as double the temperature leads to double the volume. But in general, they will expand when temperature increases. Now, I keep saying this, in general, they do that. There's one very notable exception, which is water, and we'll talk about that at the end of the section. Let's talk about linear expansion, and this has to do with solids. So you have a solid material, and you heat it up, and measuring just in one dimension, we'll call it the length, it will expand. Now, we can't talk about the linear expansion of liquids, because a liquid, it has volume expansion, but you can't simply talk about the length of a liquid because only one dimension, well, it will fit the container that it's in. But we can talk about the linear expansion of solids. Here's the equation. First of all, to the right is what I've drawn in purple. This is the equation as it's given in the book, that for a given solid, you've got the change in length divided by its original length, so delta L over L. You can think of that numerator as the proportion that it expands, divided by the change in temperature, is equal to some constant, and that's called the coefficient of linear expansion for the material. And different materials have different coefficients of expansion. That's the equation as it's given in the book, although you might find it more helpful, a slightly different variation of that equation, the one I have here to the left, and it's this, that we have an initial length and a final length. The final length, I've written it as L, the initial length as L naught. And the final length is the initial length times this thing in parentheses, 1 plus alpha, the coefficient of linear expansion, times the change in temperature. And this version of the equation is more useful if you want to simply find what is that final length. The version on the right in purple might be more useful if you want to solve for delta L over L, just to know what the proportion of the change is. So you should be familiar with and be able to use both equations. Now, before we get into what alpha is, let's talk about that delta L. Delta means final temperature minus initial temperature. If the temperature increases, that will be a positive number. And so the thing in the parentheses becomes 1 plus a positive number, and you've got this expansion. However, it will contract as temperature goes down. So if you decrease the temperature in mathematically the same way, delta becomes negative, or delta T becomes negative, and now you're dealing with 1 plus a negative number, or 1 minus something. And then you have a linear contraction. So even though we call this the linear expansion equation, it's really linear expansion or contraction, depending on what happens to the temperature. Keep in mind that there's limited scope for when this equation will work. If you double the temperature, or triple the temperature, you might end up melting the material. So this equation works as long as, you can see it's written here in parentheses, this applies for small changes in temperature. So that can even be, depending on the material, as long as it doesn't get close to melting. It can even be several hundreds of Kelvin, as long as the material itself can withstand that. But we're looking at small changes here. You're not going to double the length of a steel bar just by doing something to the temperature, because by that time, long before it gets to even close to that linear growth, it's going to just melt. The coefficient of linear expansion You can look these up in a table in the book, but here are just a few. For aluminum, alpha is 24 times 10 to the negative 6, and the units can be either 1 over Kelvin or 1 over Celsius degrees. It's being multiplied by the change in temperature, and as I've said before, if you're dealing with a change in temperature, Kelvin and Celsius are the same thing. And this refers to how much for every degree change, whether it's Celsius or Kelvin, how much the object will expand. The greater the coefficient of linear expansion, the greater expansion you're going to get. So alpha for aluminum is 24 times 10 to the negative 6. Copper is a little bit less, so it's not going to expand as much, 17 times 10 to the negative 6. Glass, particularly Pyrex, is about 3.2 times 10 to the negative 6, so it will not expand as much. Steel, 12 times 10 to the negative 6. Let's look at a problem in the book. Problem number 22 in the back of the chapter. I've solved it two different ways, so this will give you a feel for those two versions of the same equation that I gave you previously, and you can decide for yourself and discern which one you want to use in a given case. But let's look at this. Problem number 22 in the back of chapter 17 says a power line wire spans 250 meters between two support towers. The wire is made of aluminum, and on a winter day when the temperature is negative 12 degrees Celsius, the wire's actual length is 250.42 meters. By how much does its length increase on a summer day when it's 29.5 degrees Celsius? All right, here's my given information. We know it's aluminum, so we're going to use the coefficient of linear expansion. We have the initial length at a temperature of negative 12 degrees Celsius, and we have what we'll call the final length at this higher temperature, 29.5 degrees Celsius. And we want to know what its length is going to be, but more to the point, what the question is asking is by how much has its length increased? So it's actually delta L that we're interested in. I've shown you two solutions. Let's go with the first way that I've drawn it. So I'm going to use L1 equals L naught times 1 plus alpha delta T. We plug in all the values. As you can see on the page, L naught, 1 plus alpha. Delta T is 29.5 minus negative 12. And what we get is the initial length times a very small percentage above 1. And when you apply these problems, this equation, it will always be something very small, not much different from 1. If it's expansion, you see something like this, a typical value, 1.000996. If it's a contraction, you might see something like 0.9995, but it'll be something very, very close to 1. So what we get is that the final length on this summer day is 250.669 meters. We look at what did the question actually ask. It asked for by how much does it change. So we're going to solve for delta L is L1 minus L naught, subtract the two, and we get 0.249 meters or 25 centimeters. So you think 25 centimeters, that is close to a foot. That's how much this wire has increased. Now the alternate solution, because we see from the beginning that it's asking for delta L, you might want to use the equation given in the book. And you notice just looking at the writing that I've done, it took less writing to solve this alternate solution. There's less to it. So we're going to take this equation as it's given in the book, solve it for delta L. So delta L is alpha times L, which is really L naught, it's the original length, times delta T. Plug in those values, and again, you get the same thing, 0.249 meters or about 25 centimeters. Now, if a solid expands in one dimension, it's expanding equally in all three dimensions, so we actually have volume expansion. Let's now talk about volume expansion, and this also applies to liquids. So an object, whether solid or liquid, will expand based on this equation. I want you to see this equation is the same format as the linear expansion equation, It's just V's instead of L's because we're looking at volume. And there's a different coefficient of expansion. This is the coefficient of volume expansion. For solids, beta is equal to 3 times alpha. That has to do with the three-dimensional nature of this, and it takes about half a page of algebra to go through and prove that, but that it does come out to be 3 alpha. It's something you can look up in a table as well. Over to the right, I've drawn in the purple the equation as it's given in the book, that beta is the change in volume divided by initial volume divided by change in temperature. However, you might find it useful, as with the linear expansion formula, to use this one, V equals V naught times 1 plus beta delta T. Now for gasoline, beta is 95 times 10 to the negative 5. I want to compare that with steel, and I pick on steel in particular because many gas tanks in cars are made of steel, 36 times 10 to the negative 6. And so gasoline expands much more rapidly than steel, than the steel container that it's in. And that's going to be important as we go on through this section to see that sometimes when you have liquid inside a solid, they will both expand when you increase the temperature, but the liquid expands more than the solid. That can lead to trouble, but it also leads to a useful device, mercury thermometer. But we'll get to that. Water at 20 degrees Celsius. Now, water is very peculiar, and for reasons I'll get into at the end of the section, all life on Earth relies on this peculiarity of water. But look at this, water at 20 degrees Celsius, its coefficient of volume expansion is 20 times 10 to the negative 5, meaning the volume will expand at a rate of 20 times negative 5 times every degree that it goes up. However, it's changing. Now, particularly weird is water between the temperatures of 0 degrees Celsius and 4 degrees Celsius, right close to freezing. It is actually negative. Its coefficient of volume expansion is negative. Here we have water at 1 degree Celsius is negative 4.8 times 10 to the negative 5. What that means is, in this narrow range between 0 and 4 degrees, when you heat up water, if the temperature increases, it will actually decrease in volume. That's very peculiar, very strange, but as I said, as I'll get into at the end of this video, all life on Earth depends on water doing that. So because of the molecular structure of water and ice, this is how it operates. Mercury, as we use in mercury thermometers, 18 times negative 5. Compare that with glass, typically 9.6 times 10 to the negative 6. And you just see that mercury has a higher coefficient of expansion. Okay, here's some applications, some life applications. One is with your gas tank, do not overfill it. When you fill it up at the gas station, there's an automatic cutoff. So before it actually fills up all the way, the gasoline machine, the pump, it will automatically cut off. The reason is you should leave a little bit of room in that gas tank. Part of that is so that if the gas expands, there's room for that so it won't overflow onto the street. Now, gas tanks, as you can see one pictured there, tend to be made out of steel, aluminum, maybe polyethylene, and they have a relatively low coefficient of volume expansion. So you think about, you pump up your gas and the gas is kept under the ground, the gasoline at the gas station, under the ground where it's relatively cool, and I'm thinking about particularly on a summer day, and then you put in your car, and then your car sitting outside, it heats up, the gasoline heats up, and you have a situation where they will both expand, both the tank and the gasoline, but the gasoline will expand more. And if there's no room for it to expand, it might overflow onto the street, creating a mess and a waste of gasoline. A thermometer is a good, useful application. So you think a mercury or alcohol thermometer. You have a liquid, so it's got a relatively high coefficient of volume expansion, compared to the glass that it's inside, relatively low. So when it heats up, they both will expand, but the mercury or alcohol, whatever liquid is on the inside, expands more. And it expands at a predictable rate so that for a given temperature, it will expand so much, so it basically will go up. So a certain distance that it goes up, they mark that off when they calibrate the thermometer. They say this distance or this height of the column of mercury or alcohol corresponds to such a temperature, and you can make a thermometer out of that. Another application, I think of different ways to open a particularly tight glass jar, such as this jar of pickles right here. Well, jars of food, pickles, jam, jelly, things like that, tend to be the jar is glass, but the lid is metal, something like steel. Well, steel has a higher coefficient of volume expansion than glass. And so one trick for opening up a particularly tight jar is to run it under hot water. You run it under hot water, and there will be a little bit of expansion of the glass and the steel lid, but the steel will expand more. For a given temperature change, it will expand more than the glass jar. And so when it does that, it will loosen up a bit from the glass jar, and it's a wonderful way of opening that up. Now keep in mind there is danger of running hot water on a cold jar, so do not take a glass jar out of the freezer and run hot water on it. And do not take a very hot jar, maybe straight out of something glass, maybe straight out of the dishwasher, very hot, and run cold water on it. The reason is because of glass's coefficient of volume expansion, that when you run hot water, let's say we take a glass jar and it's frozen and we run hot water on it, all of a sudden at that spot, there's a sudden increase in temperature. The rest of the jar hasn't increased in temperature, but right at that spot where you're running the hot water, a sudden increase of temperature will lead to a sudden expansion right at that spot, and the glass is fragile, it can't handle it, and it can shatter. It probably will shatter if you do that. Also, a hot jar or a hot glass, you suddenly run cold water, maybe put it in ice real fast, it could shatter for the same reason. Suddenly there is a quick change in temperature, even if that temperature is going down. Okay, so there's a quick contraction of that glass, and it could shatter. Let's look at an example in the book. Talking about a few minutes ago, I was talking about spilling gasoline and why we shouldn't fill up to the very top our gasoline tanks. Let's look at example 17.5. Spilled gasoline. It says a steel gas can holds 20 liters. Okay, so about 4 liters per gallon. We're talking about 5 gallons there at 10 degrees Celsius. It's filled to the brim with gas at 10 degrees Celsius. If the temperature now increases to 25 degrees Celsius, by how much does the can's volume increase? How much gas spills out? And let's be precise with our terms. It uses the term gas. That's what we call it in our everyday language, but we're not talking about the phase of gas. We're talking about gasoline. All right, so we need steel and its beta and gasoline and its beta. We can look those up in the book, but there they are. We have V0, 20 liters, T0, 10 degrees Celsius. T1 is 25 degrees Celsius. Delta V is what we want to know. It's asking by how much does the volume change. So in this case, I think it's useful to use the equation as it's given into the book. In the book, how beta is related to delta V over original volume divided by delta T. We need to figure out both what is the change in volume of the gas can and what is the change in volume of the gasoline. Because yes, the gasoline will expand, but the expansion of the can will allow for some of that expansion. What we want to know is how much overflow there's going to be. How much gasoline will spill out? But the first question is, by how much does the can's volume increase? And that's what we need to figure first, so let's do it. The volume of the can, or the change in volume of the can, is beta V0 times delta T, and that comes from this expression where my pointer's at. So we have beta times 20 liters times the change in temperature. And let's be mindful of units. Since it's giving it in liters, I don't feel like we need to translate that to cubic meters. Let's just keep it in liters. Also, being mindful of the units. The beta, I wrote it in 1 over Kelvin. I could have just as easily written in 1 over Celsius degrees. We're multiplying by degrees Celsius or Celsius degrees, and whether it's Kelvin or Celsius, they're the same thing. It'll divide out. We're left with that the can expands by 0.0108 liters. That's the answer to the first question. Now we look at how much does the gas expand? So we have beta times V naught times change in temperature. Only thing that's changed here mathematically is the coefficient of expansion of the gasoline. We get 0.285 liters. So the can has expanded by 0.0108 liters. The gasoline has expanded by 0.285 liters. The spill, how much spills, is the expansion of the gasoline minus the expansion of the can, and we get 0.2742 liters. All right, let's talk about this peculiar thermal expansion of water. Most substances, their expansion, if we graph volume versus temperature, it looks something like this, a linear expansion related to the equation we were just using. That was a linear equation. And so it looks something like this. Water right between 0 and 4 degrees Celsius does something a little weird. You can see, looking at this chart, at about 4 degrees, it starts to increase. It's not quite linear. It'll be sort of kind of linear after about 8 or 10 degrees. But right in here, you've got this curve. So you can see water. Right here at the left, it's 0 degrees Celsius. So imagine we have just melted ice, and now it's at 0 degrees, and we continue to increase its temperature. It doesn't look like the chart up above where it starts to increase in volume. In fact, it will decrease in volume. Decrease in volume means density increases. And then it gets to its maximum density, meaning minimum volume, and then it goes the other way. It acts more normal, like most substances do. Volume starts to increase, which means density starts to decrease. Some applications of this are, unfortunately, I'll get to the unfortunate application first. When you have water in pipes or in water bottles, and they're near freezing, those pipes and water bottles can freeze, they can shatter and break. So if you take a water bottle, you put it in the freezer, and it's got no room for expansion. It's a filled water bottle. When it is freezing, so if you look at the chart, it's right here, and the water will, yes, it will decrease in volume, but then it gets past 4 degrees. Then it starts increasing in volume, getting bigger and bigger. And there's situations where it can shatter. The water gets bigger and bigger. If the container can't hold it, it will shatter. And I have shattered a few of those Nalgene bottles. They're pretty strong. They take being dropped on the ground pretty well, pretty shatterproof. But I have had Nalgene bottles, and not even full Nalgene bottles. I've had them sometimes only with about 2 inches of water. Most of it has air in it, but only about 2 inches of water, and they'll still shatter. Not that the water grows to the full capacity of the bottle, but there's something about that it sticks to the bottom of the bottle, but it'll break through down through the bottom. So you have to be careful with that. Pipes, garden hoses, things like that have water in them. You get near to freezing, and the water can expand and possibly shatter them. Down at the bottom of the page, this is very neat, and this is the phenomenon that I described earlier, is that I think all life on Earth relies on this. Life relies on the life in the oceans, and that the oceans are not frozen. We rely on that ocean water to be liquid so it can be a part of the water cycle. And down at the bottom of the ocean, here I've drawn an ocean right here. the blue is supposed to represent an ice cube. The oceans are very, very cold. On average, they are close to freezing. And down where my pointer is, it is very, very close to freezing, and the sunlight has no opportunity to warm it up. It's so deep, the sunlight effectively doesn't get down to that. If water behaved like all other materials, then it would freeze, and being frozen, a solid is more dense than a liquid. It would just settle on the bottom and you would get a layer of ice. And then the water right above it would freeze and you would get a layer of ice. And you would just get this layering of ice as water, when it gets colder, would solidify. It would grow in density and sink towards the bottom. And pretty soon, most of your oceans would be frozen and the sunlight would never be able to get to it to warm it up. But instead, a very interesting thing happens. When water starts to get near freezing, you look at this chart here, when the temperature is decreasing, it expands in volume, meaning its density gets lower. And so it will tend to float upward. It will float upward and get towards the top where the sunlight has the ability to melt it. So any water in the oceans that might possibly be freezing, they will go lower in density and come to float upward and get warmed by the sun. So we have oceans that are not freezing because of this peculiar behavior of water. That is it for section 17.3 on thermal expansion. Have a great day.